Hello, welcome back guys to Tutoring with Abdul, and today's session we'll be talking about octal numbers. Octal is a word which stands for 8, so it's any number that's base 8 is called octal numbers. So the number system that has a base 8 is an octal number. Octal number has 8 symbols starts from 0 to 7 with 0, 1, 2, 3, 4, 5, 6, 7. These are all the symbols. Any number that octal number represent, it will be using these symbols. There is no 8 and there is no 9 in this number system. Because it's called octal because it has 8 symbols, but it doesn't have a symbol for AS. It doesn't have a symbol as we use it in decimal 8 and decimal 9. We don't have them in here. Okay, so there are from octal to binary representation. From the 0 to 7 we only use 3 bits binary, because we only need 3 bits binary if you're going from 0 to 7. Number 8 will be equal to 10 base 8. For example, we say like octal is used to represent the binary numbers. Okay, when we convert octal to binary, we use 3-bit binary for each digit. Numbers such as 37 base 8, and so we can write it down. We have to refer to a table, or we can just memorize those numbers. So 3 is, for example, is 0, 1, 1, and 7 is 1, 1, 1. So that combined together, it'll give you binary representation of the 37 base 8. We said I use using 3 bits binary because it'll be easier for us, because the reason is 7 include only 3 binary digits there. So that's why we are only using 3 bits. You can use 4 bits if you want to, but 3 will be easier to do up to single digit number. So let's see what we have there. That was the example for to conversion. Just to give you a quick overview, you convert each number to its binary representation and combine them together later. Okay, so there's a table for the decimal, binary, hexadecimal, and octal number. I did it from 0 to 15 as a decimal, and this is a representation of these. So let me change the color here. I select from 0 to 7. I use 3 bits because I only need 3 bits there. But if I keep going up, like from 8, 9, I'm using more digits there. So that will be something we can concern. For example, we said 15, right? 15 base, if you want to write 15 base 8 as the binary number, we will have to convert each number to its representation in binary. So 1 is 0, 0, 1, because we said we're using only 3 digits, and 5 is 1, 0, 1. So 15 here, where is that one? So we call 1, 1, 0, 1. They're not using this 0, these 2 zeros there, but it's okay because 0 doesn't mean anything on this side. But just to make it easier for us, we are using it, so it'll be easier to represent it as an octal and binary number. So this was just an example extra. Okay, the table should be clear enough to understand what it is. What are they? All these numbers are representing in there. So let's go and work on these things. Okay, so now whenever we talk about something, we will just see, hey, why we need these numbers. Of course, there might be some conversion. We need to convert it sometime. For that part, we have a when we do talk about conversion, we have a octal to binary, then binary to octal back, then binary octal to hexadecimal, octal to decimals, and decimals to octal. You have like back and forth 6 different conversion. But if you know the base ones, which is if you can convert octal to binary, then we already learn how to convert binary to hexadecimal and binary to decimals. We can take care of that. Or if you want to learn all of them, stick around this video. We will work on all of these problems here. Okay, so shifting gears, converting octal to binary. When we converting octal to binary, we convert each octal digit to its 3-bit binary representation, which we just did an example before, like 37 base 37 base 8. We did that. So example will be here. The following octal change, convert the following octal number to its equivalent binary numbers. So let's see, 12 base 12 base 8, 207 base 8, 61 base 8, and that's back and forth. Like I got 6 example there. Let's see what we did here. As we say, we convert each digit to its binary representation. 12 base 8 is what is it equal to? So you write 1 base 8 is equal to 001 binary number, and then says 2 base 8 is 010 as a binary number. Then you combine them together, you get this whole number. 12 base 8 is equal to 1010. So 12 base 8 is equal to, as a binary representation, it should be our 10 in decimals. Okay, so this is equal to 10 base 10. Also, that's just for your ease to know what that number is. Now 207 base 8 is 207. Yeah, we say can't say that 207 because it's a different base system. It's not decimal system, so we can't use that decimal representation. So it'll be 207 base 8. So each digit you write it down and represent that from the table that I've given you here. This table you can write down like 2 is equal to 010, and 7 is equal to 111, and 0 is 0. So you can use that table to work on this problem, or you can memorize up to 7 or 10 binary numbers up to 10 counting. So 2 is 010, 0 is all zeros, 7 is 11. Combine these 3 together, you'll get this number is your binary number, and that will give you, that will be a little bit longer number to convert it to decimals, but we will work on that later. So that's how we solve this problem. So now number 3 is 61. I will do C, example C. So 61 base 8. What we will do, we know that each digit has to be converted to its binary representation. So 6 is 6 base 8 is equal to, it'll be 1 1 0, and 1 base 8 is equal to 0 0 1. Now combine them together, you will get 1 1 0 0 0 1. So that is our number as a binary of the binary representation. 61 is equal to 110001. 110001, 3 zeros. Let me straight these writings. Okay. B1 base 8 is equal to 0 0 1. Now combine them together, it will be 1 1 0 0 0 1. So that is our 61 as a 61 base 8 number representing as a binary. Now let's do one more example. Let me do F6003. Get some space here. Okay. Alrighty. So F is 6003. I hope. Yes, that's 6003 base 8. That number will be equal to binary representation, as we will see. 6 base 8 is equal to 1 1 0, and 0 is 0 0 0, and 0 is again 0 0 0, and 3 will be it'll be 0 1 1. Now you combine these three numbers, start from the first digit will be 1 1 0 0 0 0, then 0 0 0 0 1 1. So that is our binary number equal to 6003 base 8. Okay, so that is right there. Okay, so we got the number 110000000011. So we got 2 4 2 6 6 into 8 zeros, so which is 3 3 6 and 8 zeros in between, and then 1 1. Okay, and for you guys, please work on these two problems. See if you guys can solve it. If not, please comment those questions so I can work on that in a separate video if you have any concern, and we will be moving on to the next session. Now we say converting binary to octal. We just did a octal to binary. Now we'll be going back to octal from binary. I hope this shouldn't be that hard too. Now it says like when we try to convert binary to octal, we separate three digits of binary because we have, for octal we only use 3 digits. We can use more, but you only use 3 digits. It'll be easier. Binary, so we assign octal numbers and write it as a base 8. Okay, what is it saying? If we given this number, we can separate 3 digits by 1 starting from right. So 3 3 3. So we separate these numbers 3 digits and then say, hey, they can represent this. We can go to the table, find out what that number is, and you write it down like that. 111 is 7, and that is 3, and that is also 3. So it'll be 133 base 8. I hope I got it right. Not 1, I'm sorry, 7. Yes, 7. 7333. So base 8. That's what we mean. We separate all these three digits from starting from right. So we got 3 right there, 3 right there, 3 right there, and then we assign each 3 binary bits to its octal representation. Looking at the table, or you can memorize them. It's not that hard. 0 to 7 is only like 8 things to remember. It shouldn't be that bad, but you can do either way. Okay, so that's an example here. So 111 011 011. It says like write these numbers as a equivalent of octal numbers. We already did that there, but we will just try to explain it here. First thing we do, we separate 3 digits binary such as these numbers. This should be this should be a quotation, I guess. I don't want to confuse you guys. Then after doing so, we write an octal number to its corresponding 3-digit binary number, as we just said there. So 111 is equal to 7 as an octal number, 011 is equal to 3 as an octal number, and 011, same thing, is equal to octal 8, octal 3. Combine these numbers and you will get 733 base 8. 733 base 8, that's how it says. Alright, I hope it was not that bad, and let's go to the examples. Okay, let's do some example here. Welcome to the example session. We'll try to solve some questions here. Luckily it's only given 3. It says write down the octal values of these following binary numbers. So A is saying 1 0 0 1 0. To solve this one, we separate 3 digits starting from right. So there will be the first separation point. Then we only have 2. We can add 1 0 there. So this will become 0. This will become 0 1 0 0 1 0. Now, since we have 3 and 3 numbers there, we can separate and assign the value. So this number and this number. So 0 1 0 is base 2 binary. It's equal to, if you go look in that table, it will give you 2 base 8 and 0 1 0. It'll still give you 2 base 8. Combine these together, it'll give you 2 sorry, not 22 but 2 base 8. Okay, that's how we have it. Okay, that is correct. So if you're missing a digit, then you can just go ahead and just find out, add a 0 there like we just did here. You're missing a 0 because it's 1 0. This was only 5 digits, but we had to add 1 to the left side, because adding a 0 to the left side of any number, it will not change any value, but it will just give you a light up, like we're dealing with this number system. All right, let's go to the number B. B is question number B is 1 1 0 and 1 1 0 1. That's a binary number. We will have to separate three digits or 3 bits. 1 3. That's the second 3. We're missing 2 numbers or 2 digits there. We will just do that. Add 2 more zeros there. 2 0. Okay, that'll be 1 1 0 1 0. Should be one more 1. So now if you separate them, it'll be 1 3, and that's what second 3, and this is the third 3 digits. Okay, so now we can write down as its equivalent representation 0 0 1 is equal to, it's a binary number, this is a binary number. The octal representation will be 1 base 8. Now 1 0 1 is a binary number. Its representation as a base 8 will be 4 and 1 5 base 8, and 1 0 1 is same thing, base 5 base 8. Combine these together, you get 1 5 5 base 8. Okay, so that was number B. Now let's see. We will do C or we will give it to you, so it depends. So B was the number B was, the given was 1 1 0 1 1 0 1 1 1 0 1 1 0 1, which is, that's how it should be, because we need 3 digits for that, and we already had 3, and how many we had? We had 3 here, we had 3 in there, we were missing 2, so we just got 2 more digits there. 155 base 8 is equal to 0 0 1 1 0 1. Okay, 1 0 1 and then 1 0 1. All right, that should be okay. That's not bad. We can live with that. Okay, so that's we got 9 digits there. If you put that number in calculator, you will get this value: 0 1 1 0 be 1 1 0 1. Because the calculator use 8 digits, they use 4 digits representation. If it's be 4, 8, or 12 digits, so we do it manually in our hand, like on the pen, because the 3 will be much easier to deal with it, because 7 or octal number can be represented using only 3 bits binary. If it's from 0 to 7, that's how it is, like every number. Even if it's 33 7 5 8 9 9 9, there's no 9, sorry, 6 6. So that can be 6 can be represented as 3 bits binary also, and also the 6, the other number too. So we only need 3 bits, but calculator is a program to use 4 bits, so that's how they will be getting. We got 2 zeros in the beginning, they got 1 zero in the beginning, but final answer is the same. You guys please do this as a homework, solve it, and let's go. If you have any question, then please comment that question and we will talk about that. All right, let's move on. All right, our next topic is octal to decimal conversion. We talked earlier any number like this, binary to decimal and hexadecimal to decimal. What we did, we used the placing value. If it was binary, we used the binary was binary, since it's only dealing with 2 numbers, so we had a base 2. 2 to the power n was there, the placing value. If you use the hexadecimal, we use 16 to the n. N is any number starting from 0, but a non-negative number. But it's octal number here. The placing value will be 8 to the power 9. 8 to the power n, 8 to the nth power. N is any number, not any number, but non-negative. It should be positive integers. So what we do here, we're dealing with octal numbers, so that will be 8 to the power n. N is any is number of digit of octal, so that should be non-negative, by the way. It shouldn't be negative number. Once we write down the placing values, then we write the octal numbers below it. Okay, and do the following. We will demonstrate it in one example. Okay, so that's good. We will have an example here. Example, if you want to convert 4176 base 8 to decimal or base 8s, so what we will have to do, we will find out how many digits we have. We have 4 digits. We will start from 1. So that will be, let's write it down. It'll be 1 to the power. We have the 1 there. 1 to the n. No, it's not n. So it'll be start from 1, then, okay. That's actually not right. Okay, that'll be, I think it's some mistake. Yes, as it says like that, 8 to the power 1, which is, sorry, 8 to the power 0, because start from 0. Then 8 to the power 1, 8 to the power 2, 8 to the 3. So that's how we place the value. It's from 8 to the power 1 is any number. If you raise that to the 0 power, it will be 1. 8 to the power 1 will be 8. 8 to the power 2, or 8 squared, is 64, and 8 cube is 512. So you find those placing value because you only do 4, because the question is asking only 4 digits. Then once you do that, write down the numbers below the placing value. So okay, so what happened? So it was 4. The question was, where is that question? Oh, yeah, 4176. 4, write it down. Start from the left. and then 1, then 7, then 6. Once you do that, it's all base 8 number. So what you'll have to do now, the third step will be to multiply these numbers right now. 4 multiplied by 512, 1 multiplied by 64, 7 multiplied by 8, 6 multiplied by 1. Then you add them together and that will be your decimal value. So 4 times 512, 1 times 64, 7 times 8, 6 times 1. All these numbers, combine them together, that will give you 2174 at base 10. So that wasn't that bad. We will do some examples to enlighten even more. So 4176 as a decimal number is 2174. Okay, it's not bad. Let's do some examples here. Let's get some space before examples so we know what we are doing. Okay. Alrighty, solution number A. It says convert the following octal numbers to decimals. So we will solve like 3 of them, and I'll give you one to work on it. 316 base 8, convert that to octal number, the decimal number. So what we will have to do, we have only 3 digits there. We will do 8 to the power 0, 8 to the power 1, 8 to the power 2. We only need 3 digits there. So you can write it this way, or you can write it on 1s 8s 6, that will be 64s. So that will be 64s. Or you can do it time 1, time 8, time 64. Whatever you like, whatever representation you like. So you have these 3 representation, how you like it. Now, once you find the placing value, then you will have to write the individual number below that. It will be 3 base 8. And starting from left, 1 base 8, 6 base 8. The third step is to multiply these number. 3 will be 3 times 64 plus 1 times 8 plus 6 times 1. So 3 times 64 will be 3 times 4 is 12. 1 will go there. 3 times 6 is 18, will be 19. 192 plus 8 plus 6. So that will give me 206 base 10. So the number was 316 base 8 is 206 is a decimal number. So that will be okay. I believe that's fine. That's a good answer. But the procedure is to find the placing value. You can either use any of these 3 procedure. 8 to the 0, you can just find how many digits you need. You'll find that many placing value. That will be 8 to the power n, starting from 0 and going all the way to how many digits you have. And these 3 different representation, and tell you like where the placing value is. You can write it any way you want to. Then after you find the placing value, you put those individual numbers under the placing value, starting from the left here, and after that you'll have to multiply those numbers to this placing value and add these all numbers together. All right, so now let's do B. 6170 6170. B is let's do B. 6170 base 8. We have to find the placing value. it'll be, we can deal with 4 digits, will be, we can do it one, we can do 8 to the 0, 8 to the power 1, 8 to the power 2, 8 to the power 3. So that will be, we can do 1s, 8s, 64s, 512s, I believe. So that will be 512s, yes, correct. Then you write down those each individual number below it will be 6, 1, 7, 0. So what you do now, the next step is to multiply this number by the placing values of it. So if you multiply 6 by 512, it will be 6 multiplied by 512, you get 3072 plus 1 times 64 will give me 64 plus 7 times 8 will give me 56 plus 0 times 1 is 0. So now add these number. So plus 64 plus 56, so 3192 base 10, or just say 3192 number. So that was the actual number there. 6170 as an octal base or base 8 is equal to 3192 decimal number. Okay, so I solved 2 of them. I'll leave these 2 to you guys. Please solve them and see if you have any trouble doing that, solving those examples. This will be relatively easy. C will be easy. For D, you can use the same concept that I use. You only have 4 digits. For 4 digits, you have 8 to the power 0, 8 to the power 1, 8 to the power 2, and 8 to the power 3. So once you do that, place the value and place the numbers below it, and then you multiply. And the final step is add all those numbers together. That will give you your decimal numbers. All right, I hope it wasn't that bad. Okay, there is one more topic after this, converting decimals to octal numbers. After this will be only simple topics. We will discuss that and we will call the day. Converting decimals to octal, it is the same process that we did it for decimals to binary and decimals to hexadecimals. And instead of base 2 and 16, we divide the decimal number by 8. For example, 108 base 10 can be written as an octal number. So what we can do, 108, we will divide that by 8. And if you have a remainder, we will write it down. If you don't have any remainder, if you have a remainder, we'll bring that down. And the new quotient, we will divide that by base 8 or 8 again. If we have a remainder, we'll bring it down. If not, we will just bring the 0 down. Whatever the remainder is, we'll bring down that. Then after that, collect all the numbers. It is octal numbers. Okay, so just to, we can solve that concept in this example. So 108, it's a decimal number, so how can you write it down as an octal number? We will divide 108 by 8, so we get 13, a new quotient, and the remainder will be 4, so we will bring that 4 down here. So that's our 4. Then we have a new quotient 13, that divided by 8 is 1, and we have 5 remainder. We'll bring that 5 down also. So the new quotient was 1. 1 divided by 8 is 0. And we have a remainder of 1. We will bring that down. 154 is the octal number. And that is the representation of 108 as a decimal number is equal to 154 as an octal number. Okay, so it wasn't that bad. We we will just brush up because it's the same exact process that we have done it in hexadecimal and decimal in a binary system too. Alright, we have 4 examples here, and I hope I can solve 2 of them, give you guys 2 of the homework. So I'll pick and choose. I will solve this example and I will solve this example for you guys. You guys solve B and D. Okay, so solution number 1, A. It says 3134. Write this as an octal number. So what we will do, we will divide that number by 8. 3134 divided by 8. Let's do division. 3134 divided by 8. We get 391. 391, and we have a remainder will be 6. We'll bring that 6 down. Okay, now the new quotient is 391. That divided by 8 will give me 391 divided by 8 will give me 48 as a quotient. And we will have a remainder of 7. Bring that 7 down also. Now we have 48 as a new quotient. Divide that by 8. Now we will get 6. 6 times 8 is, what is that? 48 divided by 8 is 6, correct? Remainder is 0. Bring that 0 down. Now we have a new quotient 6 divided by 8 is equal to 0, and remainder will be, remainder is 6. Bring that 6 down. So we have 3134 base 10 equal to 6076 base 8. That's how we solve it. We divide those numbers and we will get finally our answer there. So there was the 3134. We get 6076 as an octal number. Alrighty, so that wasn't that tough. Let's do the example number C. We will do example C. Let's do that. Okay, so C is example C was 6178, 6178, 6178. It says like write this number as a octal number. So that's a decimal number. We will have to divide this number by 8. 6178 divided by 8. 6178 divided by 8. We get 772. And remainder is 772. So 6178 divided by 8 is 772, and remainder will be 2. We'll bring that 2 down. Okay, now we will have to divide the new quotient by 707, which is 772. That will be divided by 8 also. The new quotient will be 96, and the remainder will be 4. Bring that 4 down. Okay, so the new quotient 96 divided by 8, we will give 12, remainder 0. Bring that 0 down and write it there. Now we have 12 divided by 8, we get 1, remainder will be 4. Bring that 4 down. Now we will have a new quotient 1 divided by 8 is 0, remainder is 1. Bring that 1 down. So 6178 decimal number is equal to 14042 as an octal number. So 6178 is equal to 14042 as an octal number. Okay, so that wasn't that hard. You divide the number by 8, get the quotient, and find the remainder. Then the new quotient will be divided by 8, get the new quotient, and find the remainder and write it down. Same thing, you do it all the way until you get your quotient less than 8. And you just follow it up until your remainder become the new quotient, which is that 1 is our quotient and remainder is that 1. Or you can say when the remainder is, or the quotient is less than our divisor, so that's when we stop there, because you can't divide 1 by 8. That's 0, and that 1 will become remainder right there. Alright, so now you guys go ahead and solve these two questions. If you have any concern, please let me know. Okay, moving on to the last topic of this session will be bits, bytes, nibbles, and word and its sizes. What are these things? We've been talking about bits and some numbers. So let's see what bits and bytes, nibbles, and words are. Okay, a single binary number is called a bit, 0 or 1, correct? A single binary number, which is 0 or 1, it's called a bit. It's an abbreviation for binary digit. Binary digit, we say bit. Bit is the smallest unit of the data in the digital system, which is the smallest unit of the digital system. It's also called high is 1 or low is 0. High and low. High is 1, low is 0. Okay, there's a note that I put. Even the simplest digital devices today handle larger data group, which in computer jargon called word. That means it's the simplest, let's say, calculator or any simplest device that use a group of that use a larger group of data. In computer jargon, that is called word. The width of the main data bus is the same size of the word size. The length of the word is depending on the application of the system. Some common microprocessors have 8, 16, 32, and 64 bits data. 16 is 1 word, 32 will be 2 word, and that will be 4 words. So we will go to these things, how these represents. So a bit is either 0 or 1. That doesn't look like 0. That's 0 now. A nibble is 4 bits. A byte is 2 nibbles or 8 bits. A word is 4 nibbles, 2 bytes or 16 bits. And a double word is 32 bits, 4 bytes, and 8 nibbles. And a quad word is 64 bits. Quad means 4, yes, 4 by 16 is the 64 bits. Alrighty, so now moving on to the examples. I hope that wasn't that bad. We will just... Okay, so what is a group of ones and zeros which represent number, letter, or codes called? Um, the combination of the letters, so it's either can be bits. We can say that bits, how many bits, it depends. But with the complex system of the computer, we will call it word. Word is consisting of 16 bits, 32 bits, 64 bits. So we can call it like bits, 16 bits, I would say 16 bits word. That will represent number, letter, codes, and anything. That will be that. What number 2, example number 2, what term is used to represent 4 bits of data? Nibble. It will be nibble. Nibble is 4 bits. Okay. Now, example now 2. Below is a huge binary number. Given answer the following questions. How many bits are there? How many nibbles are there? How many bytes are there? Finally, how many words are there? Okay, so what we will have to do, since a nibble is 4 bits, we will find out how. You just have to count these numbers now. Start from right, will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 times 4 is 44, I believe. 11 times 4 is 44 bits. We got A, 44 bits. Now how many nibbles are there? B will be, nibble is 4 bits. One nibble is 4 bits. Divide that. Now since we found that 1, 2, 3, 4, 5 nibbles, 6 nibbles, 7 nibbles, 8 nibbles, 9 nibbles, 10 nibbles, and 11 nibbles. So we have 11 nibbles. Or you can divide 44 by 4 because 44 bits, and one nibble is 4 bits. It will give you 11 nibbles. Let me work on this. It will be 11 bits, 11 nibbles, sorry. Now C is asked how many bytes are there. One byte is 8 bits, so we will have a completely 5 bytes and 1 nibble. We can't say it's completely, but it's not complete byte system, but it will be 11 nibbles. Okay. And it's a full 5 complete bytes we have. 1 byte, 2 byte, 3 byte, 4 byte, 5 bytes, and be 5 bytes and 1 nibble. It is like that. Okay. Or you can also say 6 bytes, but then you have to add 0, 0, 0, 0, 0, 0, just to make it complete byte system. Now D, how many words are there? A word is 16, 32, and 64 bits. It depends what you want. So that will be 1 word here, and second word here. So like more than 2 words. More than 2 words. So one word is 16, 16, 16 will be 32, 32 and 16 will be 48. So we only have 44 bits, so we don't have 48 bits to make it 3 words, but it's between 2 and 3 words. More than 2 words, less than 3. Alrighty, so that was all from this octal number, and then finally we talked about bits, bytes, nibbles, and word. And that shouldn't be all. This was just, I added these things just for you guys to have a little bit practice. And I will see you in the next lecture. In the electronic system, digital electronic system, we will be discussing gates, logic gates. Will be coming in sometime soon. Until then, take care, guys, and I'll see you.